Hey everybody, welcome back. Hope everyone's doing well. Today what I want to do is we're going to discuss a new concept in electrostatics. We're going to be talking about electric potential and electric potential difference. This is really important because by putting all these ideas together, eventually we're going to be moving into circuits and how we could build systems in order to make electricity work for us. Oh, that went off. Okay. So in order to discuss this idea of electric potential, first I kind of want to discuss an idea that we've already talked about. Gravitational potential energy. Now, if I have this object and I move it from here up in the gravitational field, we know that it gains gravitational potential energy, right? So that means there has to be something different between this location in space and this location in space. If I was to draw, let's say we have our Earth. We know the Earth has gravitational field lines pulling towards the Earth. We're going to get back to electrostatics in a bit. But if I take a mass and I move it up in this gravitational field, we've always talked about gravitational potential energy as gaining height, but I want you to think of it as we're going against the gravitational field. By taking a mass that wants to fall down and moving that mass upwards in the gravitational field, we have to do work in order to move it against the field. So this mass, by moving it up, it gains gravitational potential energy. Now, imagine that I talked about moving a mass, but let's say we know that we can move like a 10 kilogram mass, a 20 kilogram mass, and they'll gain different amounts of potential energy depending on what mass we have. But regardless of what mass we move, there has to be something different about these two locations in space. Regardless of what mass I move up there, we have to do work to the mass to lift it up. By working that against the field, we can see that there's a difference between these two locations in the gravitational field. Okay, keep that idea in your head. Thinking about locations in the field instead of actually moving a thing throughout the field. Let's take that idea and take a look at moving things through an electric field. Let's say we have a positive test charge, and we take that positive charge and we move it from B to A. Now, if we let go of that positive test charge here, it wants to move away from that positive charge. So we don't have to do any work to just let it go and go away, but we do have to do work to take this positive charge and move it from B to A. It'll gain what we call it'll gain electric potential energy by doing work against the electric field by moving the charge from here to here. So, let's first define this idea of electric potential. We're now thinking in terms of energy for our electrostatic exploration. Electric potential is electric, can't spell, E-L-E-C-T-R-I-C, potential energy, per unit charge. What does that mean? Okay, get out of the way so you can see. But like we talked about with the gravitational field, how there's a difference between the two locations in the gravitational field, there's a difference between these two locations here, A and B. Regardless of what charge I move, whether it's a 1 coulomb charge, 2 coulomb charge, we know that there is some difference in those locations. Depending on what charge we move, it'll gain a different amount of potential energy. But let's say we ignore what charge we're moving and we're just looking at the differences between these two locations in space. Electric potential energy per unit charge means we're dividing out the charge. So if we don't care what charge we move, we're only interested in the difference between these two locations, we can call that difference between this spot and this spot, these two differences in electric potential, we call that potential difference. potential, did I spell it right? Hope so. Difference. Okay. So we're looking at these two different locations. And if I were to move a charge from here to here, we know it would gain potential energy. There's a difference between these two locations, and we can actually calculate the difference. We call that potential difference. The reason why we ignore the charge is because we're interested in those two locations, and if I were to put a charge there, or if I was to move a charge there, how much energy would it gain? By thinking in terms of energy now, we could start thinking about how we could put these charges to work. And if we understand how these different locations work, again, it doesn't matter what charge I put there, we have a better understanding of the difference between those two locations there. So we're not usually interested in electric potential for a single spot. We want to know the difference between the two spots, right? Just like if I was holding an object some height above the earth, I'm more interested in the difference between moving those two locations than I am about just holding it in this one spot here. Thinking about how much energy it could gain or lose. All right, so potential difference has a long definition, but we'll talk it through. This is the work or energy required per unit charge to move a charge. Just move it around on me. From one point to another in an electric field. Gotta hold this. Okay, so if I were to move some charge from B to A, we're interested in how much energy it would gain if I were to put a charge there. But we're not putting a charge there, we're only looking at the difference between these two locations. That's why it's the work or energy per unit charge required to move some charge from B to A. We're looking at the difference in those two locations, how much energy we would need if we were to take a charge and move it between those two places. It's kind of tricky to wrap your head around, but once we start doing examples, I think hopefully things will start making sense. Okay, so we're looking at those two locations, the work energy per unit charge. So our equation is the work or energy per unit charge. How much energy we require if I were to put a charge there, okay? And we call this potential difference, the letter we use for potential difference, you guessed it, capital V. Okay, so this capital V is what we call potential difference. There we go. Okay, and this is work or energy. And this is charge. Again, we're looking at the property of the location. There's no charge there, but if I were to put a charge here and move it, how much work or energy it would require. Okay, so we measure work or energy. I can't spell, G-Y. There we go. Okay. Now, we measure work and energy, as you recall. This is where I would ask you in class, what do we measure work and energy in? But you can answer me. Work or energy is measured in joules, as you recall. Charge is measured in coulombs, those are the SI units. So we could measure potential difference in joules per coulomb. But the SI unit we don't use joules per coulomb. We actually use what we call volts. Now we're getting to the words that you're probably familiar with, that you've heard when you've heard some kind of electricity concepts. These ideas of volts, amps we're going to be talking about in the future. But we measure potential difference through volts. Joule per coulomb. So 1 volt is equal to 1 joule per coulomb. Okay. Now, we want to think, what kind of quantity is this? Is this a vector quantity? Does it have direction? Or is it a scalar quantity? If you recall, work and energy was a scalar quantity. We're only interested in the amounts that we had. Charge is a scalar quantity. Charge doesn't have direction. It has types, which we call positive and negative, but it's still a scalar quantity because we're not interested in what direction the charge is, just what charge we have. So if we take a scalar, divide by a scalar, this is going to be a scalar quantity. Okay. I'm going to say it again because it's a tricky concept. It's the difference between these two locations in space. If I were to take a charge, move it there, how much energy would it require to move whatever charge I choose? By understanding how these two different locations work, we can better understand how charges would move if we were to put them there, how the energy works for electric fields and such. I don't know, pause the video, write this down, take a break, I don't know. I'm gonna erase this. So as always, when it comes to thinking these things through, it's kind of tricky to think about this in the abstract. So let's dive into some questions and see if we could work out, if we could predict things like energy, potential difference, and charge if we have the right given quantities. Let's try some problems. There we go. Here's question number 1 that we're going to work through. It takes 16 joules of work to move a 2 coulomb charge from point A to point B. So we want to know the potential difference between points A and B. So the only thing we know is how much work it required to move this 2 coulomb charge. The fact that work was done means that we know that this 2 coulomb charge had to be moved through this electric field. Now keep in mind, this is assuming that this charge is positive. If this charge was negative, you'd actually have to do work to move the charge with the field. Because remember from our last video, positive charges want to move with the field. If I let this positive charge go, it's going to want to go this way. So I have to do work to push it against the field. But with this negative charge, if I let this go, it's going to want to go this way. Right? Because it wants to move against the field. So I actually have to do work to pull it with the field. We don't know what type of charge we have, positive or negative. So either two of these situations could be happening here. Keep that in mind. So we know how much work we have to do to move this charge through this electric field. We want to know the potential difference between those two locations in space. We could use this information, and by understanding the potential difference between these 2 points, then it doesn't matter what charge we have, we can better understand how these 2 locations work electrostatically, if that makes sense. Okay, so let's use our new equation. We know that potential difference, V, is equal to work per unit charge, Q. Okay, now our goal is to find this potential difference. We know that it took 16 joules of work to move this 2 coulomb charge from point A to point B. So working this out, simple division, 16 divided by 2, we know that the potential difference between these 2 points is 8. Our unit is volts. We don't have to write out the word volt. We can actually just use capital V for volt. So the potential difference between the 2 points is equal to 8 volts. Driving math teachers crazy. V equals 8V. Remember that this means potential difference. This means volts. Now, by understanding, now it doesn't matter what charge I move. The potential difference between these 2 points is always going to be 8 volts. And that's useful knowledge for us. Doesn't matter what charge we have. We now understand those 2 locations in space now. Good? All right, I'm going to erase. How you guys feel about this? Feeling all right? I'm a YouTuber now, so leave me a comment, like and subscribe. Okay, let's try another question. Now, I want to know how much work will it take to move an electron across a potential difference of 1 volt. So let's say we have some location A and B in space. We know the potential difference between those 2 points is 1 volt. No matter what charge we have, that's the potential difference between those 2 points. It's the property of the locations. So I want to move an electron across this distance, and how much work is it going to take? Going back to our equation, V is equal to W over Q. Our goal is to find the work. We know the potential difference between those 2 spots is 1 volt. But what's the charge on an electron? At this point, hopefully you know that you can look at the reference table, page 1. The charge on an electron is 1 elementary charge, which is equal to 1.6 times 10 to the minus 19 coulombs. You know you're officially a physicist when you have these crazy numbers rattling around in your head. Okay, so we're moving this electron through a potential difference of 1 volt. We can multiply, and we find that the work required is equal to, this times 1 is just itself in magnitude, 1.6 times 10 to the minus 19 joules. Okay, now this quantity is actually important for us. We're going to be defining a new way to measure energy. When it comes to electrostatics, we're often moving tiny little charges, a single electron, or microcoulombs, nanocoulombs. So very often it doesn't make sense to work with these really crazy numbers, times 10 to the minus 19. So this energy, the energy required to move an elementary charge through 1 volt of potential difference, we call an electron volt. An electron volt, even though we're saying volt, it's a measure of energy. This is very important. Volt is potential difference. This is not energy, just a property of the location. But this value here, 1.6 times 10 to the minus 19 joules, is equal to 1 electron volt, a measure of energy. Let's define this. An electron volt which we use little eV, is gonna get low over here. The work or energy required. It's all moving around on me. To move, feels ridiculous right now. To move 1 elementary charge through a potential difference of 1 volt. Okay. I'm going to say it again because it's very important. An electron volt is a measure of an amount of energy. The amount of energy required to move 1 elementary charge through a potential difference of 1 volt. Now you might be asking yourself, why bother with this new unit? Why are we going to try to confuse ourselves? Again, when we're working with very tiny charges, an elementary charge or just a few multiples of an elementary charge, it makes much more sense to talk about them in terms of electron volts than it does to talk about them in terms of joules. If you look at things like the Large Hadron Collider, when we're measuring energies of colliding particles at super high speeds, we often talk about the energies in terms of electron volts because it just makes much more sense to talk about electron volts than it does to talk about joules on the order of 10 to the minus 19. It's kind of like using kilometers. You can say 3 kilometers instead of saying 3,000 meters. There's just another way to talk about an amount of stuff we have that's easier to communicate. All right, write this down. Pause the video, I'm gonna erase. So let's use this electron volt. And compare it to joules. Actually, I want to take this, there we go. So for our next 2 problems, 3 and 4, for 3, we want to know how much work in electron volts does it take to move a proton through a potential difference of 250 volts. And for number 4, we want to know how much work in joules does it take to move a proton through a potential difference of 250 volts. Both of these questions are calling for you to solve for the work or energy required. This one wants you to report that work or energy in electron volts. This one wants you to report that work or energy in joules. Let's start with number 3 first. And again, to reiterate, this 250 volts between, let's say, point A and B, property of the location, doesn't matter what charge, the potential difference between these 2 points is always 250 volts. Okay. So, for number 3, we know potential difference V is equal to W over Q. Another thing you might be wondering is, well, when we talk about electricity, we often talk about voltage, but you never hear this idea of potential difference. Potential difference and voltage are technically the same thing, but we tend to use the term potential difference when we're talking about electrostatics, so we can better define the term. And then when we get to circuits, you're going to hear me using potential difference less, and you'll hear me start using the term voltage a little bit more. Okay, potential difference is work over charge. We want the work in electron volts. If we want our answer to be in electron volts when we solve for the work done, we want to plug in elementary charges for Q. Okay, so before I plug in, I'm just going to write this down. If you want work in units of electron volts, use units of elementary charge for Q. What does that mean? Well, we usually, the units we usually use for Q is coulombs. We measure charge in terms of coulombs. But if we want our work, our energy to be in electron volts, instead of reporting in coulombs, report to me how many elementary charges we're actually moving. If we're moving a proton, that's a single elementary charge. So for Q, instead of plugging in 1.6 times 10 to the minus 19, we're just going to plug in 1 elementary charge, or 1e. Okay, So our potential difference is 250 volts. We want the work done. We want this work done in electron volts, so I plug in 1 elementary charge. That's the charge on a single proton. Okay, 250 multiplied by 1. We get our work done to be 250 electron volts. That's a lot nicer to report, saying through 250 electron volts instead of using some kind of crazy number that you're going to see next, which will be on the order of 10 to the minus 17 joules. Okay. Now for number 4. We now want this to be in terms of joules for number 4. So if you want your answer in joules, don't plug in elementary charges for Q. Actually plug in coulombs for Q. How much charge you have in coulombs. If you want work in units of joules, use units of coulombs for Q. Okay. All right, let's work this out again. We have 250 volts. We want work in joules, so we're going to be plugging in coulombs down here for charge. A single elementary charge, again using page 1 of the reference table, we know is 1.6 times 10 to the minus 19 coulombs. I'm plugging in coulombs because I want the work done, the energy, to be reported in joules. When you work this out, make sure you do this on your own, on your calculator, to make sure you're getting my answers, and you can do this yourself. But I got an answer of 4 times 10 to the minus 17 joules. 1.6 times 250. Double check my work. I can always make mistakes. For some reason, I feel like I made a mistake here, but just double check. I'll make sure I let you guys know if I made a mistake. So again, notice this energy is reported in joules. This is a crazy small number, times 10 to the minus 17. It's much easier to report things in electron volts when we're dealing with these tiny charges. All right, pause the video, write this down, and I'll erase. We'll go on to the next thing. There's a few more things I want to discuss. So while I'm erasing, that term volt, it's pretty crazy that we, just the word volt makes you think of electricity, but volt actually is named after a dude. Forgot what his first name was, but his last name was Volta. He was an Italian physicist, and he did a lot of work with electricity. His last name was Volta, so he used volts in order to, what's the word? Tell him how good of a job he did. Volts for Volta. Okay. Now, I want to talk about question number 5. 2 more questions to go. We're almost done. You guys are doing a good job. 5 and 6 are also connected. We have a particle with a charge of 4.8 times 10 to the minus 19 coulombs, and it's accelerated from rest through a potential difference of 100 volts. What is the particle's final kinetic energy? I hear what you're thinking. Mr. Hatzfeld, we haven't talked about kinetic energy. Remember that if it's starting from rest, the amount of energy we gained that this particle gained was the work done to the particle. So check this out. We know potential difference is equal to work per unit charge. Our goal is to find kinetic energy, but if we find the work and the particle started from rest, the work done on the particle is equal to the total gain in kinetic energy. Remember, those old physics concepts don't go away. The work energy theorem tells us the amount of work done is the amount of energy that the particle gained. This particle gained all kinetic energy. So if we know the work, we know the final kinetic energy. So, plugging this in, we know that the potential difference between the locations is 100 volts. Is equal to, our goal is to find the work. The charge is given to be 4.8 times 10 to the minus 19 coulombs. Okay, I'm plugging in coulombs because we're going to get our final kinetic energy in joules. If it doesn't specify, or if it gives you the charge in coulombs, you could just report your work done or your energy in joules. This times 100, it works out to be 4.8 times 10 to the minus 17 joules. Now, just a quick little tangent. If I wanted to report this in electron volts, on the front page of your reference table, it tells you how many joules is in a single electron volt. So instead of going back and plugging in elementary charges and working it through again, you could just simply take this number, do some dimensional analysis. You can say 4.8 times 10 to the minus 17 joules. Go to the front page of your reference table, you'll see that you'll see that 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. Doing some dimensional analysis, we can report this answer in terms of electron volts. This question doesn't ask you to do that, but this is another way to switch from joules to electron volts and back. Again, electron volts is a measure of energy, not of potential difference, even though the word volt is in the title. Okay. Erasing that, moving this over, rolling right along. So we know how much work was done to this particle. And this work, because it started from rest, the amount of work done is equal to the gain in kinetic energy of this particle. Okay. So this doesn't seem like a lot of energy, right? 4.8 times 10 to the minus 17 joules. But what's really cool, the next part of the next question here is talking about this here. If the particle has a mass of 2 times 10 to the minus 27 kilograms, which when we're dealing with subatomic particles, they often have masses this small. We want to know the final speed that the particle is moving. So again, the story. We put this particle at rest in this electric field, and it got accelerated through this potential difference. We want to know the final kinetic energy of the particle. We have the kinetic energy. Let's see how fast it's going if we know its mass. Okay, thinking back to energy, you should know that kinetic energy is equal to 1/2 mv squared. We know the kinetic energy that gave us the mass. You should remember that this is our equation for kinetic energy. We can use kinetic energy to find speed. That v is speed. Let's plug in what we know with units. We know the kinetic energy is 4.8 times 10 to the minus 17 joules. 1/2, the mass is given to be 2 times 10 to the minus 27 kilograms. We want to solve for this v. Don't forget the square root. Work this out in your calculator. I'm serious. Pause the video, work this out, look at the number, and try to make sense of what that number is. I'll wait. Videos are weird. Okay. When you work this out, you should get a speed of about 2.2 times 10 to the 6th power. And that's in meters per second. That is 2,220,000 meters per second, right? Because if we move this over, 2,200,000 meters per second. Think of how long a meter is. A meter is about 3 feet. This particle is covering about 6 million feet per second. That's how fast this particle is moving. With this tiny amount of energy for these tiny particles, they can achieve pretty high speeds. Something to keep in mind, this speed is on the order of 10 to the 6th. The speed of light, the fastest thing in the entire universe, is on the order of 10 to the 8th. It's not that far off. You take this and multiply it by 100, we're getting pretty close to the speed of light. This particle can never beat the speed of light, but we can get these tiny particles to move very close to the speed of light in places like the Large Hadron Collider. Or even naturally, cosmic rays in the universe, particles can move very, very quickly. All right. Is that it? That's it. In my notes, I actually wrote the answer and fast. Remember, it's moving fast. Okay. So that's potential difference. You guys can now work on those questions in your Castle Learning, looking at the potential difference between two locations. You should be able to work through that entire Castle Learning yourselves. If you want a little side story, I'm pretty much done here, but I'll tell you a little story about electricity. It's on my mind. There was an Italian guy by the name of Luigi Galvani. If you might have heard in chemistry things being like galvanized, that's named after this guy, Luigi Galvani. And one of the most famous experiments that he did was this guy, Luigi Galvani, would shock frog legs. This is when electricity was still very mysterious to us. We didn't really understand what this idea of electricity was. And when he shocked frog legs, the frog legs would actually start kicking and twitching. We understand today how muscles work, how it's an electrical impulse to actually move our muscles. But back then, that was really scary. Imagine you had no idea what electricity was. We're shocking these disembodied frog legs and they start kicking around. We thought that electricity might be able to bring things back from the dead. That experiment and the big public outroar when that happened actually inspired Mary Shelley to write Frankenstein, using electricity to bring back people from the dead. So it's a link to your English class or whatever. All right, that's enough for me. Hope everyone's doing well. Again, try the Castle Learning and let me know what you need. I'm making these videos, I'm working through the content, but if you guys need to see some topics over again, if you want me to work through some particular problems, if I get a lot of questions for a particular Castle Learning problem, I'll work through that in a video. But give me some feedback. Let me know how this is working for you guys. I hope it's working out under the circumstances, and hope everyone's doing well. And I'll see you soon.